Hi, my name's Nicole Fry, and this is my video for Lab 2, Motion of a Falling Object. The purpose of this lab is to observe the motion of a free-falling object initially at rest and to understand through computational modeling and comparison the forces acting on the system. So first I captured the motion of a paper ball, mass of 4.5 grams, falling from the height of 1.676 meters to the ground. I used the video and uploaded it into Tracker in order to obtain the paper ball's position through the time interval in which it was falling. Once I obtained my initial data, I used GlowScript to write the code that would create two computational models of my observations. Both computational models will be based on the physics principles of Newton's second law. The first one will have the system interacting with only the weight force of gravity, while the second computational model will both include the weight force and the drag force. The comparison portion of this lab will consist of plotting first the observed position versus time, which is obtained through Tracker. Then the predicted position versus time from your weight force computational model, and then also the predicted position versus time from the weight force and drag computational model, and these will all be on the same graph, and this will be done through Excel. Like I previously mentioned, I used a Tracker program to extract the position of the paper ball over time. My time interval was 0.767 seconds. In order to specify the length scale of the video, I used a calibration stick to set the endpoints to the length of the blue tape that is shown in the image to the right, and it had a known length of 1.624 meters. Additionally, the coordinate system also had to be defined. For this video, it was defined as the floor would be the x-axis, while the trajectory of the ball fell along the positive y-axis. The main changes done to the starter code consisted of defining the initial conditions and implementing Newton's second law into the iterative calculation. As you can see on the slide, the ball's mass was put in kilograms, and then the ball's position vector and velocity vectors were also defined. The ball's position, it started 1.676 meters above the ground or the x-axis, and then the ball's velocity is 0 because the ball was dropped from rest. Also, gravity had to be defined as 9.8 meters per second because we are dealing with a force acting on our system, which is the weight force, which is mass times gravity. And then also the j-hat vector was defined as 0, 1, 0 as a unit vector for the positive y-axis. For the while loop, as you can see, Fnet had to be defined as mass times gravity times the j-hat vector, and then the Fnet value was assigned to the variable w. Additionally, for the updates for both the object's velocity and the object's position, those were implemented using Newton's second law algebraic expressions. So in this slide here, you can see that the program has run and it has constructed a computational model based on the physics principles of Newton's second law, or equivalently, the momentum principle, that includes only the effects of gravity or the weight force. When you plotted both data sets side by side, the observational and the first predicted computational model, for time that is small, the computational model did a reasonable job at predicting the object's motions. However, as time got larger, the model predicts the object to fall farther than what it was observed. This suggests that the object's motion is affected by an additional interaction with the surroundings. This additional interaction is the force exerted on the free-falling paper ball by the air, otherwise known as the drag force. So this leads us into the second portion of the lab, which was creating the code for the second computational model, which accounted for both the weight force and the drag force. So for the code in this section, the initial conditions did remain the same. However, B, the proportionality constant for the magnitude of the drag force, was now specified as an initial condition for this part of the experiment. I determined B by setting it to a value and changing that value until my computer model's final position for the paper ball was closer to the position that was initially observed. The biggest change consisted of expressing the new calculation for the Fnet acting on the system, which in this case includes both the weight force and the drag force. Both these forces will be specified inside the while loop, and both of these forces will add up to the final Fnet used in the iterations. How we calculated this was taking two variables, W and FD, and assigning them as each individual force, and then adding them together to get the Fnet. So after having run this program, here's a constructed computational model based on the physics principles of Newton's second law, or the momentum principle, that included both the effects of gravity, also known as the weight force, and that of air resistance, which is also known as the drag force. With all the datasets graphed side by side, we can clearly see that the predicted data created with GlowScript that modeled both the force of drag and the force of weight on the free-falling paper ball was a more accurate model than that of the predicted data that only accounted for the force of gravity acting on the paper ball. However, there is a small graphical deviation between the predicted force of weight plus the force of drag and the observational data that must be recognized. This could be due to the over or underestimated proportionality constant for the magnitude of the drag force, which is our B constant. So now let's talk about the discussion questions. If we examine the velocity versus time predicted by the models with and without drag, which of the models would predict a terminal velocity? So I think that the second prediction computational model of the graph is the one that I would predict to show the paper ball traveling with a constant velocity or terminal velocity. I think this because if you look at the graph on the right, you can see in the position versus time graph that the slope is linear, which indicates a constant velocity. To understand terminal velocity, we must understand that the motion of a falling object with air resistance, drag, as well as the force of gravity acting on the system, has that the acceleration is equal to the difference of these two forces divided by the mass. But when the drag is equal to the weight, the acceleration becomes zero, and therefore you have a constant velocity. Okay, so now imagine if the object was initially thrown downward, would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So throwing it implies you're imparting some initial velocity to it. Dropping it starts the velocity at zero. So although the thrown ball initially is moving faster than the dropped one, they're both accelerated by gravity at the same rate. So if you know this, then you can apply the logic that we had in the last question to this question. Given enough time, the terminal velocity for the object would still be the same regardless of the fact that it was thrown. The slope of the position time graph would still be initially steeper, however it would even out over a larger time t.